Alright, so today we're doing the notes for 15.1. We're evaluating logs. Before we get started, we're going to spend just a couple of seconds talking about what logarithms are and why we need them. So let's say you were doing the problem 3 to the x is equal to 9, and you were trying to figure out what x is equal to. Well, you would say x is equal to 2, right? Because 3 squared equals 9. What about if you had, let's see, 3 to the x is equal to 27? Well, if you stop and think about that one, x would equal 3, right? Because 3 times 3 times 3, 3 to the third power gives you back 27. What if you had 3 to the x is equal to 1? Well, that one, remember, anything raised up to the 0 power equals 1. So you'd get x equals 0, right? Because 3 to the 0 equals 1. But what if you had something like 3 to the x is equal to 25? Well, that's different, because you know it can't be 2, and you know it can't be 3. Do you see how 25 is in between 9 and 7? Well, what that means is that when you're doing this problem, x, the number that's up here in the exponent, is going to be something between 2 and 3. It's going to be a decimal. And so what logarithms do is it gives us a way to solve the problem, to figure out what the exponent is when the exponent is not a whole number. So in order to be able to find out what that exponent is when it's not a whole number, logarithms were developed. Looking at the difference between logarithmic form and exponential form that are given to you right here, the b that's down here on the bottom, that's called the base. And it's also, if you look at it over here, it's also the base over here when it's written in exponential form. And so it's nice. So the base of the exponent stays the base in when something's written in logarithmic form. So that's nice too. And then the y that's right here is called the argument, not like when you're arguing with somebody. And then the last part of it over here, the x is the exponent. In logarithmic form, it's not written up in the power though, so that's something you want to practice. And so one of the things that you want to take away from this part of the notes, the logarithmic form gives us a way of figuring out the exponent, right? Because the exponent on that example that we talked about earlier on the post-it note was the thing we were trying to figure out. So one of the things that you want to kind of get cemented into your brains is that logs equal exponents. So when something's written in logarithmic form with this operation of a logarithm being performed, the number that comes after the equal sign is the exponent. So in these first examples, what you're being asked to do is you're rewriting the logarithmic expression into exponential form. So when you do that here, remember, so let's say this out loud together. So it's log base 3 of 81 equals 4. And remember from up at the top, right, logs equal exponents. So when I rewrite this in exponential form, log base 3, so the 3 is going to become my base. It's a big 3 now though, right, because I'm trying to write it in exponential form. So log base 3, logs equal exponents, and so that means the 4 goes up here in the exponent. Log base 3 of 81 equals 4. The argument here is that it equals 81. It's helpful to stop and think and make sure you put these numbers in the right order. 3 to the 4th does equal 81, and so this is a true equation. Same thing on b. So log base 2, big 2, logs equal exponents, so the 3 comes next, and then it's equal to 8. So log base 2 of 8 equals 3, 2 to the 3rd equals 8. It's helpful to notice that the base comes first and the base comes first, but then the exponent comes second when you're writing it in exponential form, so it's good to notice that change. Same thing with these last two. So log base 5, logs equal exponents, so 5 to the 0 power equals 1. And then lastly, log base 16, so 16 raised up to the 1/2 exponent. Remember, a 1/2 exponent is the same thing as taking the square root of the number, and that equals 4. So in this example first here, we rewrote logarithmic equations into exponential form. Now in the second example, we're going to go through and we're going to do the opposite. So these 4 are all given to you in exponential form, and so we're going to rewrite them in logarithmic form. So on these ones, you're going to be introducing the log. So all of them are going to have a log. Remember, the base of the exponent becomes the base of the log. So log base 5. logs equal exponents, so the 3 here is going to actually go at the end. The 125, the argument, that's going to come first, and then logs equal exponents, so the one that was up in the exponent goes after the equal sign. Log base 5 of 125 equals 3, because 5 to the third equals 125. So log base 2, remember logs equal exponents, so the 5 is going to come at the end. Log base 2 of 32 equals 5. Log base 7, remember logs equal exponents, so the 0 is going to come at the end. So log base 7 of 1 equals 0. And then for this last one, log base 25, remember logs equal exponents, so the negative 1/2 is going to come at the end. So this is 1/5, and it equals negative 1/2. Log base 25 of 1/5 equals negative 1/2, because 25 to the negative 1/2 would equal 1/5. So in the next example, what we're doing is we're evaluating these logarithmic expressions without using a calculator. But when you see the word evaluate, it means you're trying to determine some numerical value for the answer to the question. So let's read the first one out loud. It says log base 8, 64, and then there's no equal sign and there's no other number. Remember from before that logs equal exponents? So one thing you can do to help yourself with these, if you want to, is you can put an equals x. This is actually asking you to figure out a number that's the answer to the question. So we're not just rewriting it, we're actually trying to evaluate it. So we're trying to figure out what this is equal to. Remember that logs equal exponents, right? One way that you can help yourself when you're doing these problems is you can switch them to exponential form. And the real reason that you would do that is because you're more comfortable with exponential form than you maybe are with this logarithmic form that we're just learning about for the first time. So if you rewrote this using x, right, logs equal exponents, so log base 8 of 64 is equal to, I'm not sure, you would say 8 raised up to what exponent is equal to 64. Now, there's a couple of ways that you can proceed with this. A lot of people at this point can just stop and think about what exponent do you raise an 8 up to turn it into a 64. And if it's a whole number, then you're able to answer the question. Sometimes it can be a fraction, sometimes it can be a 0, sometimes it can be a negative number. We'll practice all of that. And so you stop and think, and you say 8 raised up to what exponent gives you 64. And so your answer for this one, right, would be 2, because 8 raised up to the second power gives you 64. Now, one thing I wanted to note, do you see how I don't write x equals 2 on my answer? I just write regular 2. That's because back up here on the top, we just used the x up here, like we added that into the problem, right, to help us answer the question. X wasn't actually an original part of this question. So if someone else looking at this problem, if you wrote x equals 2 and this was the original question, right, it would be kind of confusing where the x came from. So normally when we do these, if we use an equals x to help us, right, so on this one it'll be log base 3 of 27 equals x, so logs equal exponents 3 to the x equals 27, right, and then you can stop and think, and you're trying to think about what exponent do you raise a 3 up to get 27. So 3 times 3 would only be 9, but 3 times 3 times 3 would be 27. So I'm not writing x equals 3, I'm just writing regular the number 3 to get the answer to this one. And so that's the value of this. Even without the x here, that's still the value of this expression. So you're evaluating them. As we continue through the rest of these, there's just sort of like little differences that come up with them. In this first one here, so if we follow along with that same pattern, 6 to the x power is equal to 1. You stop and think, what number do you have to raise anything up to get a 1 out as your answer? And so for that one, the value of that would be 0. As a matter of fact, anytime this number right here is a 1, it's going to equal 0. D is a little bit trickier. We're going to have to stop and think maybe a little bit harder on this one, right? So 25 raised up to some exponent gives you out a positive 5 for your answer. So you have to stop and think about what kind of exponents make numbers be smaller. It didn't create a fraction, so it's not a negative exponent. But for this one, the x, the number got smaller, but it stayed positive and it stayed above the fraction bar. So for this one, the number that you're missing, the number that the value of this one would be positive a half. Remember that a half in an exponent is the same thing as taking a square root, right? And so the square root of 25 would equal 5, and so that would give you the value for this one. Similarly on this one, so 8 raised up to what exponent gives you a 2, you have to stop and think, it's not creating a fraction, so it's not a negative exponent. but the number is getting smaller, and so you have to think about, how does an 8 turn into a 2? Well, the cube root of 8 gives you a 2, and so for this one, the number that you're missing would be positive 1/3 as a fraction, because 8 raised up to the 1/3 exponent would give you out a 2 as the answer to the question. It's different when the number flips to the other side. And so with these ones, sometimes you have to stop and think a little bit more about them. So 4 to the third gives you 64, but do you see how the 64 winds up on the bottom on this one? And so that's how you know for this one that the answer, it's getting bigger, right? Because for 4 to turn into a 64, it wouldn't be a fraction in the exponent, but it would have to be a -3 up here in the exponent, because that would move the value of 64 down to be a division. Okay, let's see. On this one, we have 1/5 raised up to the x exponent equals 25, and so on this one you have to stop and think a little bit further as well. 5 squared gives me a 25, but do you see how the 25 is in the top of the fraction, not in the bottom of the fraction? That means that in order for the 25 to move up to the top, the exponent right here would have to be a -2, because that would give you a squared on the 5, and it would require it to move to the top of the fraction as well. Let's see. 81 raised up to what exponent gives you positive 1/3? And so for this one, again, you're stopping and thinking. Whatever number you get does move down into the other side of a fraction, so you know your x is going to have to be negative for that movement to occur. And then the other thing for this one that you need is the 81's getting smaller, so this one's going to be negative, and it's going to be a fraction. Tricky, right? For this one, you're going to get -1/4, because the 4th root of 81 gives you 3, and then the negative would move it to the other side of the fraction. On letter I, right here on this next example, this one's tricky, and it requires a little bit more understanding of exponents to help you understand the answer to the question. So we started out the same. We say 2 raised up to what exponent gives you -4, and then at that point, it's helpful to stop for a minute and kind of think about this question. So 2 raised up to the first power would equal 2. 2 raised up to the second power would equal 4. 2 raised up to the third power would equal 8. So do you see how all of these answers that you're getting out right here are positive numbers? That means that there's not going to be a positive number you can put in for this exponent to get out a -4. Let's see, what about 2 to the 0 gives me 1, so that one doesn't work. And then the other thing you want to consider is what happens when you plug in negative numbers. So let's say you did 2 to the -1, that would give you 1/2. 2 to the -2 would give you 1/4. 2 to the -3 would give you 1/8, then they would continue. And so if you look at all of these numbers that you're getting out, do you see how none of them ever wind up being negative? There's no number that you can raise a positive number to in an exponent to get out a negative number. And so for this one, we say that it's undefined, because again, there's not a number that you can raise a positive base up to get out a negative value. Lastly, on J, you're asking yourself, what number do you raise a 5 up to get out a 5? And so you stop and think. And so for that one, x equals 1, because 5 to the first power equals 5. So the value of this would equal 1. As a matter of fact, anytime the base matches the argument, it's always going to equal 1. Over here on the notes in the next example, it talks about a common logarithm. And so anytime you see a log without a base, that base is 10. It also talks about natural logs, and so ln of x is defined as being log base e of x. And we haven't done a lot of work with e in our course, but we'll be able to see what that looks like here moving forward. So in this first example here, when it says log of 100, remember that means log base 10 of 100. And then if it helps you, you can always include the equals x. Remember, we're evaluating, so we're trying to figure out the value of this expression. So 10 raised up to what exponent equals 100, and then you can stop and think about that one, and you think, how many times do I have to times 10 by itself to turn it into a 100? And so for this one, the answer would be 2. So log of 100, or log base 10 of 100 would equal 2, because 10 squared would equal 100. Same thing on this one. So log of 1000 means log base 10 of 1000, which means 10 raised up to what exponent gives you out 1000 as the answer. You stop and think. 10 times 10 times 10 gives you 1,000. And so the answer for this one would equal 3. When you see these ln's, ln is defined as being the natural logarithm. And so you see up here how it's log base e. Remember, e has a value of about 3. And so we'll practice more with e in this course as we move forward in practicing these natural logarithms. So when it says lne means log base e of e. And again, you can put the x if you want to. And so that means e raised up to what power gives you back e. And so then you stop and think. Anything raised up, anything to get itself back out, right, is always going to be the power of 1. And so this equals 1. It's actually really important that you remember that anytime you see ln in a problem, ln is always going to equal 1. So the natural log of e will always equal 1. Same thing. So on this one, the natural log of e to the 4th is going to be log base e of e to the 4th. And so that means e to what power is equal to e to the 4th. The bases are the same, which means that the powers are the same. And so for this one, it equals 4. And then the last two in this example are just variations of the same thing. So log base e of e to the square root of 7. It's kind of just putting in a different number instead of the numbers that you're used to. So e to the x is equal to e to the square root of 7. You stop and think. When the bases are the same, it means that the exponents are the same. And so this would equal the square root of 7. And then lastly, on this one, you see how the 2 is out front. So we're just going to do all the work on the natural log of e, and then we'll wait on the 2. So it'll be 2 times log base e of e. Now if you want to put the equals x on this one, you would have to put it over here and kind of ignore the 2 for a minute to continue your work on this one. But I wanted you to recall that back over here, we did say that anytime we had ln e, it would equal 1. And so log base e of e raised up to what power gives you back e, this is going to turn into a 1. And then 2 times 1 for this one will give me 2. So again, anytime you see natural log of e, that's always going to equal 1. And then that'll give you your answer to the question. The final example on this notes page is asking us to practice using a calculator. It's okay if you don't have a graphing calculator with you. You can do this using the calculator on your phone, or you can also use just a web-based calculator, like the Google calculator has these buttons. So you see here where it says log, and you see here where it says natural log. So the log and the ln buttons on your calculator are going to be over here off to the side if you're using a graphing calculator. And then on your phone calculator or on a Google calculator, just make sure that you indicate that you can find where those buttons are. We're going to be solving equations with these in a coming section in this chapter, and so you want to make sure that you know where to find them. So when you do these, you're just typing them into a calculator or to a computer. You just want to make sure that you get comfortable with how you type them in. So when you type in log 13 and you hit the enter button, it gives you a decimal approximation. So remember, log without a base means log base 10. So this is actually telling you what number exponent, right? Logs equal exponents. So this is what number exponent you would have to raise a 10 up to get out 13 as your answer. So you see it's a little bit bigger than 1, but not quite 2, right? Because 10 squared would be 100, and you're only trying to get 13. So it says to round it to the nearest thousandth. Thousandths means 3 decimal places. So this one's going to be 1.114. And then after I do that one, I'll do the natural log of 13. And you get a different number, but that makes sense, right? Because natural log is log base e, so this is what exponent you would have to raise. E is a little bit less than 3. It's what exponent you would have to raise a 3 up to, a little bit less than 3 up to get 13 out as your answer. So it makes sense that it's bigger than 2, right? Because 3 squared would give you 9, but it's smaller than 3 because 3 to the third would give you 27. So that's going to be 2.565 because the 9 will have the 4 round up. And so to finish out the rest of these questions, remember you're just typing the work into the calculator. So the common log of 7, or log base 10 of 7, would be 0.845 when you round it. And then same thing, the natural log, or ln of 7, would be 1.946 with this one rounded up. And then you would type these just into a calculator as well. So you're doing the common log of 1.4 and then the natural log of 1.4. So 0.146 and then 0.336 for this one. It would not round up. So this was just calculator work to kind of get you ready for the next section, the sections coming where we're going to be doing some evaluating and solving.